Okay, we're going to try to go through the remainder of this paper, question 17 onwards. So I think the last question is numbered 19, 17, 18, 19 on the visualizer. So hopefully it will work well. So this is about projectiles. It reads as follows. A distress flare may be launched from a boat to signal for help. A flare was launched, okay, from a stationary boat, so the boat's not moving relative to the sea, at an angle of 30 degrees, so I've drawn that in, to the horizontal. The flare was launched to the right of the boat, from the launch position marked X on the boat in the diagram below. So they've given us all that. You just have to complete the diagram to show the path taken by the flare before it hits the sea. So basically they just want you to show the kind of path, the parabolic shape, starting off at an angle of 30 degrees with the initial velocity u in a direction that they've told us, which is the angle of 30 degrees. That's all we know. Okay. It then says, so that's part one is just simply drawing the parabolic shape, and you'll get a mark for that. The next one, so I would give myself a mark for doing this. The maximum height of the flare above the launch position was 42 meters. Well, that's going to be in the middle of the flight going up. So that will be the 42 meters that they're referring to. That's the maximum height. So that I put that as displacement vertical being 42 meters. I then put down everything we know. At that position, the vertical velocity here, so v vertically will be 0 at that height, because up and down it's going to go, slow down to 0 and then fall back down due to the gravitational forces involved. So the vertical velocity final will be 0. The initial velocity vertically will be the component of u upwards. So that would be u sine 30. If you can't do this kind of trigonometry, you just need to go and revise that. Or what I always tell my students, if you're going through the angle given, you put cos. If you're going against it, you go sine. I'm not going to explain the trigonometry at this stage. Okay, so once we know that, the other thing we know is the acceleration is due to gravity, and it's in downwards, so everything else upwards is positive, and downwards is therefore negative because these are vector components. So show that the flare was launched at a speed of about 60 meters per second. In other words, we want to show that u was approximately 60. So we know v, u, s and a, so we use the equation v squared equals u squared plus 2as. Put the numbers in, use just as I've drawn on the right, as I've listed them on the right of my page. U sine 30 squared, the final velocity will be 0, and you add 2 multiplied by minus 9.81 because it's acting against the motion, multiplied by 42, which is the maximum height at the center of the flight. Okay, once you do that, you will find that the answer comes out, if you follow my trigonometry, 57.4 meters per second, which is approximately 60 meters per second. So you'll get probably a mark for this, a mark for putting the numbers in, and a mark for knowing that you're using the correct equation. Okay, that's the model answer for this first part of question 17. Okay, so the next part of question 17, part 3. It says the flare was visible from a maximum distance of 8 kilometers, and a rescue boat was 8.2 kilometers from the boat in distress at the time of the launch of the flare. That's what they mean. You have to determine whether the flare traveled a sufficient distance to be visible from the rescue boat. You should assume that the flare was launched in the direction of the rescue boat. Okay? In other words, did the flare travel a horizontal distance sufficiently? That means greater than 200 meters, because it's currently 8.2 kilometers from the boat. If it travels 200, then it will reach the 8 kilometers, which will make it visible to the rescue boat. Okay, so we want to know, is the horizontal, we want to know if the horizontal distance traveled is going to be approximately 200 meters or more. Okay, so step one is to find the time the flare is in the air for. So I always explain to the students the easiest way is to look at the horizontal motion, just like we did before. We want to know the time. So if we still know the same data from before, the vertical velocity was 0, the acceleration was minus 9.81, and we know the initial velocity horizontally, just like in the first part that we just calculated as part 2, the vertical velocity initially was u sine 30. So we use the same things. This time we got v, we got u, we got a, and we got t. This is the simplest way. It doesn't involve any squares. So you work out the time to reach the maximum height using this equation. I've rearranged the formula to put t as the subject of the equation. Put the numbers in. V is 0 minus the initial velocity, u sine 30, divided by the acceleration due to gravity, which is acting against it, and you will have the following algebra. Comes out to 0.293 to 2 decimal places. If you do it more accurately, that means the total time that's in the air is twice that time, because it takes the same amount to come down as it took to go up. So the answer is about 5.852. Okay, so that's the total time that it's in flight. Once you know the total flight time, you can work out the horizontal range, which will be S horizontal is this time it's the component of the initial velocity, u, but this time it's cos 30. Remember I told you if you want to go through the angle, the horizontal component will be u cos 30. If you're going vertically, it will be u sine 30. Okay? So once you got that, the time is given here. We just calculated with our vertical information. The horizontal range will just simply be the answer to this number. It comes out to approximately 291 meters. Therefore, the flare will have traveled enough distance, i.e. greater than 200 meters, to be visible from the rescue boats. That certainly is one of the marks. I think this question is 4 marks. So you will see where you get the mark, one for working out the time, one for this. It will be something like that. Okay, I haven't looked at the mark scheme. I don't want to spend too much time on that. You can find the mark scheme just by looking for the mark scheme for this particular year. It's not a year which is hidden, so you can find them. It then says, state one assumption you've made in our answer for A part 3. Well, it's always the same assumption with projectiles. We always assume the air resistance is negligible, which means it can be ignored, which means the horizontal velocity is constant. Yeah, it's not being slowed down. So in reality, of course, there will be some air resistance. As I always tell my students, A level is a simplification of reality. Okay, so that's the end of question 17. Over the page, we have a question about conservation of momentum. So this time, a game is played where each player must use a mallet. A mallet is like the kind of thing they use in, what's that game where you hit the balls, croquet. Yeah, so it's like a wooden hammer-shaped tool to hit a disc across a table. So this time, here's the mallet. So anything that's producing a force can then move the disc. So that initially, the mallet is the only thing moving. The disc is stationary before the collision. One player accidentally lets go of the mallet. The mallet then travels at a speed of 1.6 meters per second. So that's the u initial speed of the mallet. I put it as um, and collides with the stationary disc here. After the collision, this is this diagram, after the collision, yeah, the mallet continues in the same direction at a lower speed. So it's lost some of its momentum from 1.6 velocity to 0.3. So the momentum is lost by the mallet, will be gained by the disc. The disc moves in the same direction as the mallet with the velocity v as shown. So this is, we know that we need to know the mass of the disc. So that could be md. okay? And we want to find the velocity, d. So it says calculate a value for v. V, in this case, they mean velocity of the disk. All the other velocities given, the masses are given. So it says mass of the disk is 0.035 kilograms, so that's the mass of the disk. I'm calling it md. And the mass of the mallet, yeah, is given here as 0.17 kilograms. So the conservation principle, conservation of momentum principle applies. That means the sum of, this symbol sigma means the sum of the momenta before the collision must be equal to the sum of the momenta after the collision. Well, the momenta before was the mass of the mullet times the initial velocity of the mullet plus 0 because the disk wasn't moving. So at the end, they're both moving, so you have the mass of the mullet times the final velocity of the mullet plus the mass of the disk. These are given to us. The only unknown is v. Okay, so I like to show my answers algebraically first. I've made v the subject of the equation, so I've taken away this from both sides. 0 can be cancelled, so then you got this minus this divided by the mass of the disk. Once you then do that, all the numbers are given. You should be able to stop the video and work out where the numbers came from. 0.17 was the mass of the mullet, yeah. 0.16 was the initial velocity of the mallet here, minus the final velocity of the mallet. That's the momentum lost by the mallet divided by the mass of the disk, and you'll get 6.3 meters per second. Again, understanding that you have to use the principle of moments, and working out the algebra correctly will get you the marks, 3 marks. Okay, so once you do that, apologies, I just need to zoom in again. I'm still getting used to the software. Okay, so I'll physically move it closer to the visualizer camera. So this time it says to reach the goal. This is the goal, as in a football goal. In this case, it's an ice kind of, presumably it's on ice or on a frictionless surface, or a low friction surface. To reach the goal, the disk must move up this ramp. Okay, so here's the ramp, which is at an angle of 30 degrees to the horizontal. Okay, so all I've written there for you underneath is that sine of 30 will be equal to the height gained, yeah, divided by the distance gone up the ramp. So we can have this distance and we can have the height. So if you want to work out the height, yeah, to reach the goal, the disk must move up a ramp, which is an angle there. Well, to get that much energy, we need to double check that it has enough momentum. So this is just algebra, so we're going to come back to that. So I'll put that to the side and show you the next part of the answer. Okay. It then says the velocity of the disk at the bottom of the ramp is 5 meters per second. Okay, well that means u is 5 meters per second at the bottom of the ramp. Okay, so if I just show you the diagram again, at the bottom of the ramp here, u is 5 meters per second. Okay, so we want to know, does it have enough momentum to get up the ramp? The disk moves up the ramp and work is done by the disk against the frictional forces. So there is some friction. So work is done, that means W, work done, is force, frictional force, times the distance up the ramp, which I've shown on the previous diagram. The disk moves up a distance, delta S, of 6.5 centimeters up the ramp before it moves back down. Okay, determine the frictional force acting on the disk. Okay, so we know it's gone a distance of 6.5 meters per second, and we know that this is a conservation of energy situation. So the kinetic energy at the beginning, the u was 5 meters per second, the mass we know from before. is equal to the potential energy gained, which is a delta H, which I've shown you algebraically in the diagram before. Delta H can be calculated using trigonometry as being the ramp distance, which is given as 6.5 centimeters. That'll be 10 to the minus 2 meters multiplied by sine 30. And by the way, sine 30 is always half, so they like using that number in exam questions. And F delta S is the work done by the friction or against the friction. So that's what's happening conceptually. Then we can show that the equation for F, remember we want to find out the frictional force, determine the frictional force. So that's what we want to do. So I put F on the left-hand side. That means it's kinetic energy minus potential energy gained. And remember we said delta H equals delta S times sine 30 from my earlier diagram. So this algebraically you can simplify. It may look more complicated to you, but this is the neatest way algebraically of showing it. I've put mu squared, the 2 is the half. M is common to both, so you can use it just once. And then I've got minus g delta H to be the rest of the potential energy. So the answer will come out to, just put the numbers in, m is 0.035, the velocity was 5 meters per second, and there's the divided by 2 for the half in the kinetic energy equation. Put the values in. Don't forget to multiply by 10 minus 2, which I nearly did. So it's easy to make these kind of mistakes where you lose marks. The force will then come out to 6.6 newtons. Okay? So that's question 18 done. And again, if you want to get a bit more detail on it, you can look at the mark scheme. Finally, we're on to question 19. And question 19 is about a transmission of electricity, the lines between the pylons. So they're using these wires. So this brings into consideration the forces involved, the weight of it. Obviously, they have these cables, and it brings in materials as well to help you understand what's happening. So it's to do with like materials, Young's modulus, stretching materials under tension. The transmission of electricity over long distances requires a conducting cable. That's this. That is suitable to hang from support towers called pylons. You've all seen them. The vertical distance from the line of support, to the lowest point of the wire is called the sag. They've labeled it for you. So obviously it sags due to its weight. Due to the high voltages involved, the cable must maintain a minimum distance from the ground for safety reasons. So they say that we need to have a minimum height between the sag point. Okay, so there's a weight obviously where you can assume it's acting through the center of the cable. That's the center of its mass. So I put it down as mg, and there's 2 bits of tension pulling at an angle to the horizontal, the dotted line. So you can get some kind of understanding of what's happening in terms of forces. The temperature and the tension in the cable both affect the sag. Okay, so as it gets hot, it expands, and of course that will then make it sag more. And obviously the tension is what's holding it up. Suggest one further factor that may increase the sag of a cable. Well, that could be any reasonable suggestion. If you have time to look at the mark scheme, do so, and then you will see what they've put in. In fact, I'll try to do that while I'm waiting. I'll have it up on my other screen. So this is question 19. Question 19, part A, the reasonable answers. The distance between the pylons, that will affect it, they're saying. The length of the cable that you choose. So these are acceptable common sense answers. The weight, the mass, the density of the cable material. So any of those will get you that 1 mark. Okay? So they're just trying to see, it's just a common sense situation whether you can put something sensible down. It then says, a cable of mass m at an angle theta to the horizontal, the theta is shown in the diagram, it would be symmetrical. Explain why the tension of the cable decreases as the sag increases. Well, I've put as the sag increases, it's further down, therefore theta increases. Okay, if that happens, also sine theta will increase. Okay, remember sine theta, when theta is 0, sine theta is 0. When sine theta becomes 1, when theta becomes 90, which is not going to happen. Okay, so it's going to vary between 0 and something less than 1. mg will approximately equal to twice the tension. So tension sine theta again. If you're going, you want the horizontal component of the tension, okay? And that algebraically is 2t sine theta, okay? So t is approximately therefore going to be equal to mg divided by 2 sine theta, yeah? Just changing the subject of the formula. Therefore, as theta increases, tension decreases. You can see that theta and sine theta are directly proportional, and tension and sine theta are inversely proportional. So as theta increases, tension decreases. So it says, explain why the tension decreases as the sag increases. That's your answer for the 3 questions. Okay? We'd have to look at the mark scheme to see how the marks are awarded. Yeah? Basically, 1 mark for this, definitely. 1 mark for doing the inverse proportion, and 1 mark, I suppose, for realizing that there is the natural correlation, that the theta increases, the sag increases. Okay, so that's 19 part A. Part B are giving you some information about what the cable is constructed of. Type of conducting cable used in the overhead lines is called ACSR. Yeah. We don't need to know what that means. This cable has a steel core, so that'd probably be core steel, I don't know, surrounded by strands of aluminium. So aluminium steel combination of the same diameter. That's what they're saying. So steel is in the core, so they mean the diameter of the cables, aluminium cables, of the same diameter as the steel core. Okay, so obviously aluminium is lighter than steel, so that decreases the weight problem, and steel gives it the strength that it requires. Stress strain graphs for samples of steel and aluminium typically used in each strand of the cable are shown. So you've got the steel properties of stress against strain. So this is a Young's modulus topic that you must have studied before. And the aluminium, you can see it's not able to take the same stress, or doesn't have the same stress as the steel. So it's, steel is stronger. Show that the Young's modulus of the steel is about 2 times 10 to the 11 pascals. Okay, so how do you do Young's modulus? It's stress over strain. So for a straight line portion of the graph, so that's the only bit. So I've drawn a tangent. That's what you should do. Draw a tangent for the straight line portion of the graph. For the straight line portion of the graph, it starts curving about here. So straight line portion of the graph is the initial gradient. Once you do that, you take values. I took values at 400 and used this point here on the graph. So 400 here, and whatever this value is there, 0.0025. So it's 400, but it's mega, so it's times 10 to the 6, and it comes out to approximately 1.6 times 10 to the 11 pascals, which gives you an answer approximately equal to 2 times 10 to the 11. Okay, so one is for working out from the tangent, the gradient at the initial part of the graph, and then taking the correct values to come close to 2. Okay. Finally, the last page of the exam, and as you go to the exam, the questions do get more complicated. So the pylons are positioned every 270 meters. They're giving you that distance. I've called it x. Show that the stress in a strand of steel is about 70 megapascals. So stress is force over area. Okay, these equations are given to you on the data sheets. Yeah, so you can see the data sheet at the bottom. It's got about materials, Young's modulus. You need to become familiar with your list of data, formula and equations which are given to you. Okay, so you want to show that across the A is the cross-sectional area is given as 2.3 times 10 to the minus 6 meters squared, and the tension per meter for steel is 0.62 newtons per meter. So obviously we got 270 meters of the distance between them, well, that'll be the minimum amount of steel. If it's very, very tight, it will reach exactly across. It'll be 270. So this will be the minimum tension. So this is our F in stresses force over area is the tension that was felt. So you put 0.62 times 270 on top, divided by the area given, and you'll see that it comes to approximately 72.8 megapascals, which is approximately 70 megapascals, which is what they wanted you to show. Okay, so that's how you get the 2 marks. It then goes on to look at the final part of the questions, which is usually a little bit more of evaluation of numbers. So it's kind of a skill that they were seeing if you have. The cables that we talked about, the ACSR cables, consist of a steel core surrounded by strands of aluminum cable, as explained before. The extension produced due to the tension for each strand of aluminium is 0.95. So that's the delta X, whereas before, so that's what we got, 0.95 meters delta X for that length that we're using. Comment on why these cables consist of both a steel core and strands of aluminium cable. You should include a calculation as part of your answer. Okay, so comment on why they have them. So you have to use your graphs. They want you should use a calculation as part of your answer. That means they want you to use the graph. So here, the extension produced is 0.95. So use graph to find strain on the steel graph at approximately 70 megapascals, which is what we worked out in the part above. So we find out that the strain, on that is approximately 0.0005. Let's just have a look at the graph. At 400, at 70 megapascals. So at 70 megapascals. That's what we're looking at. So 70 is very low, so we're talking about 0.01 more decimal place than shown on the strain axis. So 70 is really around here, 100 is there, so 70 is about there. So that's what they want you to show, what it is on the steel graph. So for 70, you go down and you're saying it's about a tenth of the way to 0.005. Therefore, it will be 0.0005. That's the strain. Okay? So again, remember what strain is on the equation sheet. Strain is the delta X divided by the X. So there's the equation given to you. Once we know that, for this strain, therefore the delta X should be equal to the X times the strain. So we want to show that it is approximately that value. So 270 meters times that gives you a delta X of 0.14 meters for the aluminium, for the steel. So the steel is only stretching 0.14 meters, whereas the aluminium, it's going to stretch much more. Delta X for steel is much less than the aluminium value, which were they given. So we calculated for steel using the graph. Therefore, the steel would sag much less than the aluminium. It would hold the aluminium up effectively. So that's how I've put it. So the question was you to comment on why you use both. They don't want you to just pluck it out of thin air. They want you to use, they say that you should include a calculation. That means they don't want you to just hazard a guess. They want you to prove why they do that. You can see the steel is much, much stronger. It doesn't stretch. So it will basically hold the cable up. The steel is the strong part of it. And it says, what I put here is you can also see the remarks in the examiner's report for conclusions, also has useful exemplar answers from students. And I haven't got time to go through it now because I have to produce another document. So if you want to look at the examiner's report, often they give you some insights which the mark scheme doesn't give you. Well, that's the end of this paper. So this was the paper which was never used due to COVID. It was the 12th of May was meant to be put out. They then ended up not doing the exam that year due to COVID. The fact that people were doing home learning a lot. So they actually used it in October 2020. So if you're looking for this paper, it may come under October 2020 instead of May 2020. Okay, if you found this useful, please like and share the video so we get some more people getting to use the answers. And please subscribe if you want to know when the next video will be ready. I'm currently doing another video for Unit 2, will probably be next, okay, for those of you who are getting ready for Unit 2 in the summer. Okay, I know a number of students will have to retake Unit 1, so there'll be videos on Unit 1 as well. Thank you very much for watching.